Long before rockets pierced the sky, Mars lived in the human imagination as a wandering red light among the stars, glowing softly yet mysteriously, and ancient civilizations from Mesopotamia to Rome watched it move differently from the fixed stars, calling it a sign of war because of its blood-like color. And even today, when we look up from Earth and see that reddish spark, we are seeing a real world, a planet that orbits the sun just like our own, sitting as the fourth planet from the sun, after Mercury, Venus, and Earth, placed between Earth and Jupiter in the vast stretch of space. And its average distance from the sun is about 228 million kilometers, while Earth's average distance is about 150 million kilometers, which means Mars is farther from the sun and receives less sunlight and heat. And the distance between Earth and Mars is not fixed because both planets move in their own orbits like runners on different tracks. So sometimes Mars is about 56 million kilometers away at its closest approach, and sometimes more than 400 million kilometers away at its farthest. And this changing distance has shaped every dream of reaching it, because even at its closest, it would take months of travel with current rocket technology, and yet this small red world has become the main target of human dreams of colonizing another planet, especially in recent years when people like Elon Musk have spoken boldly about building cities there. But before we imagine cities and domes, we must first understand what Mars truly is, not as a fantasy, but as a real planet with its own history, landscape, and harsh reality. Mars is smaller than Earth, about half the size and diameter, and its gravity is only about 38% of Earth's gravity, which means if you weigh 100 kilograms on Earth, you would weigh only 38 kilograms on Mars. And this lower gravity could make humans feel lighter, but it also raises questions about long-term health, because our bones and muscles are built for Earth gravity. And scientists have already seen how astronauts lose bone density and muscle strength in microgravity aboard the International Space Station. And although Mars has gravity, it is weaker, and no one yet knows exactly how living for years in that gravity would affect the human body, especially children if they were born there. And as the camera of our imagined film slowly moves across the Martian surface, we see a cold desert world, dry and dusty, with giant volcanoes and deep valleys, including Olympus Mons, the largest volcano in the solar system, nearly 3 times taller than Mount Everest, and Valles Marineris, a canyon system so vast that it would stretch across the United States if placed on Earth. And these grand features tell us that Mars once had powerful geological forces, and scientists believe that billions of years ago Mars may have had liquid water flowing on its surface, with rivers, lakes, and perhaps even shallow seas, because orbiters and rovers have found clear signs of ancient riverbeds and minerals that form in water, and this discovery changed everything, because where there's water, there's the possibility of life, at least microbial life. And so Mars shifted in our story from being just a red desert to being a world that might once have been alive. But today Mars is cold, with average surface temperatures around minus 60 degrees Celsius. And in winter at the poles, it can drop below minus 120 degrees Celsius. And its atmosphere is very thin, about 1% as thick as Earth's atmosphere, made mostly of carbon dioxide with very little oxygen, which means humans cannot breathe there without full life support systems. And because the atmosphere is so thin, it cannot hold heat well, and it also cannot protect the surface from harmful radiation, from the sun and from cosmic rays. And on Earth, we're protected by our thick atmosphere and strong magnetic field. But Mars lost most of its magnetic field billions of years ago, and without it, the solar wind slowly stripped away much of its atmosphere, turning what may once have been a wetter and warmer planet into the cold desert we see today. And as our story continues into the 20th century, humanity began to move from dreaming about Mars to actually reaching it with machines, starting with flyby missions from the Soviet Union and the United States during the space race. And although many early missions failed, each failure taught engineers new lessons. And in 1965, NASA's Mariner 4 sent back the first close-up images of Mars, revealing a cratered world and shocking those who had imagined canals and civilizations. And over the decades, more orbiters and landers followed, including Viking in the 1970s, which searched directly for signs of life but found no clear proof. and later missions like Spirit, Opportunity, Curiosity, and Perseverance roamed the surface like robotic explorers, analyzing rocks and soil. And with each mission, our knowledge grew stronger and more detailed, like a camera zooming in and sharpening its focus. As the 21st century advanced, private companies entered the story, especially SpaceX, founded by Elon Musk, who openly declared that humanity must become a multi-planet species to survive long-term dangers such as asteroid impacts, global wars, or climate disasters. And he proposed building large reusable rockets capable of carrying many people and tons of cargo to Mars. And the development of rockets like Falcon 9 and Falcon Heavy proved that reusable boosters were possible, reducing costs significantly. And then came the Starship project, designed as a fully reusable spacecraft system that could carry over 100 people at a time. And in our cinematic story, we see giant stainless steel rockets rising from launch pads, representing a new chapter where Mars is no longer only a government project, but also a private vision driven by bold ambition. Yet colonizing Mars is far more complex than simply landing people there, because survival on Mars requires solving many deep challenges. And the first is transportation, as a trip to Mars using current chemical rockets takes about 6 to 9 months one way, depending on planetary alignment. And during this time, astronauts would be exposed to microgravity and radiation exposure in deep space is a serious concern because without Earth's magnetic shield, high-energy particles can damage cells and increase cancer risk. And engineers are studying ways to shield spacecraft using water, fuel, or special materials, but no solution is perfect yet. And then there's the problem of landing on Mars, which is surprisingly difficult because its atmosphere is too thin to slow down heavy spacecraft easily with parachutes, but thick enough to create dangerous heat during entry. So landing large cargo safely remains one of the biggest engineering puzzles. And although NASA has landed robotic rovers successfully, landing humans in large habitats will require much more powerful and reliable systems. Once humans land, the next challenge is life support, because Mars has no breathable air, no liquid water on the surface, and extremely cold temperatures, so colonists would need pressurized habitats, possibly built underground or covered with Martian soil to protect against radiation, and they would need systems to produce oxygen, recycle carbon dioxide, purify water, and grow food. And scientists are experimenting with growing plants in simulated Martian soil and using hydroponics to reduce dependence on Earth supplies. And one idea is to use local resources, a concept called in situ resource utilization, where carbon dioxide from the Martian atmosphere could be used to produce oxygen and even fuel through chemical processes. And NASA's Perseverance rover has already tested a small experiment called MOXIE, which successfully produced oxygen from carbon dioxide, showing that it is not just a dream, but a technical possibility. Food production is another major issue, because transporting all food from Earth would be extremely expensive and risky. So settlers would need greenhouses with controlled temperature and light, possibly using artificial lighting power by solar panels or nuclear reactors, and water could be extracted from underground ice deposits that orbiters have detected, especially near the poles and in certain mid-latitude regions. And if water can be reliably accessed, it can be used for drinking, growing crops, and even making rocket fuel by splitting it into hydrogen and oxygen, which is central to SpaceX's plan of refueling starships on Mars for return trips to Earth. But even if technology can solve air, water, and food, there are psychological challenges because living on Mars would mean extreme isolation, small communities, limited social contact, and a harsh outside environment that cannot be entered without protective suits, and communication with Earth would have delays of between 4 and 24 minutes one way, depending on distance, which means real-time conversation would be impossible, and emergencies would have to be solved locally without waiting for instructions from Earth. And this requires highly trained and emotionally strong individuals. And long-term studies in Antarctic bases and space stations show that isolation can affect mental health, causing stress, depression, and conflict if not carefully managed. As our story moves forward, we must ask whether colonizing Mars is just daydreaming or truly possible with today's science. And the honest answer lies somewhere in between, because the physics of traveling to Mars is well understood, and we have already sent many machines there. And we know how to keep humans alive in space for months, as seen on the International Space Station. But we have never built a self-sustaining colony beyond Earth. And that is a much higher level of difficulty because it requires not just survival for a short mission, but the creation of a stable society with industry, medicine, education, and possibly even governance. And economic questions arise as well, such as how such a colony would support itself financially, whether through mining rare materials, scientific research, or becoming a backup for human civilization. Terraforming Mars, or changing its environment to be more Earth-like, is sometimes mentioned in bold speeches, but current science suggests that warming Mars and thickening its atmosphere would require enormous amounts of energy and resources beyond our present capabilities, and even if possible, it would take centuries or thousands of years. So early colonies would almost certainly live inside controlled habitats rather than walking freely under a blue sky. And yet history shows that what once seemed impossible can become reality over time, just as powered flight was once a dream before the Wright brothers, and landing on the moon was once science fiction before Apollo 11. And so Mars colonization may follow a similar path of gradual progress rather than sudden transformation. In the final scene of our ongoing film, we see Earth rising in the Martian sky as a small blue star and a small human settlement glowing under protective domes, not as a giant city, but as a fragile beginning. And whether this becomes a thriving second home for humanity or remains a scientific outpost depends on technology, political will, international cooperation, and careful planning. And so colonizing Mars is not pure fantasy, nor is it guaranteed destiny, but it stands at the edge between dream and engineering, between imagination and calculation, and the upgrades in rocket reusability, life support systems, robotics, and resource utilization show that the path is being built step by step, yet the challenges of radiation, gravity, cost, psychology, and sustainability remain powerful obstacles, and humanity must decide not only whether it can go to Mars, but whether it should. And if it does, it must go with wisdom, patience, and respect for both the red planet and the blue one it leaves behind. Because in trying to become a multi-planet species, we may learn more deeply how precious and rare our home world truly is. Imagine the year is not far in the future, and the world is watching another massive rocket standing on a launch pad, taller than any building nearby, shining under the morning sun. And this rocket is not just a machine, but a symbol of human courage and risk, built on decades of research by space agencies like NASA and private companies like SpaceX. And when people like Elon Musk speak about sending thousands or even millions of people to Mars, the vision sounds almost unbelievable, yet behind the speeches there are engineers calculating fuel ratios, life support cycles, radiation shielding thickness, and launch windows with extreme precision, because going to Mars is not about bold words alone, but about mathematics, physics, and survival. And the launch window itself is a key part of this story, because Earth and Mars align favorably only about every 26 months. Meaning if you miss the window, you must wait more than 2 years for the next efficient chance. And this alone shows how patient and carefully planned such missions must be. And once the engines ignite and the rocket rises, the journey begins with powerful acceleration that pushes astronauts back into their seats with several times the force of gravity before the booster separates and falls back to Earth for reuse, which is one of the major upgrades in modern spaceflight, because reusable rockets reduce cost dramatically compared to the old days when each rocket was thrown away after one flight. As the spacecraft leaves Earth orbit and heads into deep space, the travelers enter months of weightlessness, floating inside a carefully designed habitat where every drop of water is recycled, every breath is monitored, and every system has backups, because in deep space there is no quick rescue, and the radiation problem becomes serious, as solar flares can release bursts of high-energy particles that may damage electronics and human DNA. So spacecraft designers consider storm shelters inside the ship, surrounded by water tanks or fuel which can absorb some radiation. And scientists are also studying new materials and even magnetic shielding concepts. But none of these solutions are simple or light, and every extra kilogram increases launch cost and complexity. And this balance between safety and practicality is a constant struggle in mission design. Meanwhile, on Earth, mission control teams monitor telemetry, while families wait and watch, knowing that communication delays mean that even a short message from Mars can take many minutes to arrive, and this delay changes human psychology because astronauts cannot simply ask Earth what to do in every emergency. They must be trained to act independently, making decisions that could mean life or death. And this requires a new kind of explorer, part scientist, part engineer, part medic, and part leader. And in this sense, colonizing Mars is not just a technical challenge, but a human challenge of character and teamwork. When the spacecraft finally approaches Mars after months of travel, the red planet grows larger in the windows, no longer a bright, but a world with visible dust storms swirling across its surface. An entry into the Martian atmosphere begins, which engineers call the most dangerous phase, because the spacecraft must slow down from extremely high speeds, and heat shields must withstand intense friction while guidance systems adjust the angle of descent, and then parachutes may deploy, followed by retro rockets firing to slow the vehicle further before landing on dusty ground. And for small robotic missions, this has been achieved several times. But landing heavy human transport vehicles requires scaling up these systems greatly, which is still under development, and any failure during this stage could mean total loss of crew and cargo. After landing, the first priority is establishing a safe habitat, and early missions would likely bring prefabricated modules that can be connected together, pressurized, and supplied with power from solar arrays or small nuclear reactors. Because solar power on Mars is weaker than on Earth due to the greater distance from the sun and frequent dust storms that can block sunlight for weeks, as seen when the Opportunity rover eventually lost power during a massive global dust storm. And so, reliable energy systems are essential for survival. Powering air recycling units, water purification systems, heating equipment, and communication arrays. And engineers are also exploring the idea of building habitats using Martian soil itself through 3D printing technologies, creating thick walls that provide radiation shielding and insulation, reducing the need to transport heavy materials from Earth. Water extraction becomes a daily task, with machines drilling into icy ground deposits and melting the ice for use. And this water supports drinking, hygiene, and agriculture itself would take place in controlled greenhouses where temperature, humidity, and light are carefully managed, possibly using LED lighting tuned to plant growth needs, and crops like potatoes, wheat, and leafy vegetables might be grown, recycling nutrients from waste in closed-loop systems. And this closed-loop idea is critical because resupply from Earth is expensive and slow, so the colony must aim for increasing self-sufficiency over time, gradually producing more of its own food, oxygen, and even construction materials. Yet even as technical systems operate, the emotional story unfolds, because living on Mars would feel both exciting and lonely, with wide, open red landscapes stretching beyond the habitat windows, silent and lifeless, and settlers might step outside in protective suits, feeling lighter under the weaker gravity, seeing the sun appear smaller in the sky, and watching tiny blue Earth as a distant star at night. And such moments could inspire awe, but also deep homesickness, because Earth is not just a planet, but the cradle of human culture, oceans, forests, languages, and history. And Mars offers none of these comforts naturally. And so building a healthy community would require creating social structures, shared activities, art, music, education for children, and fair systems of governance to prevent conflict. Economically, questions arise about why humanity would invest trillions of dollars into Mars colonization. And supporters argue that new technologies developed for Mars could benefit Earth, improving energy systems, recycling methods, and sustainable agriculture. While critics argue that resources should first solve problems on Earth, such as poverty and climate change. And this debate is part of the story too, because colonizing Mars is not only a scientific project, but also a political and ethical one, requiring global cooperation rather than competition, since the risks and costs are enormous. Some scientists also raise concerns about planetary protection, meaning that if microbial life ever existed or still exists on Mars underground, human colonization could contaminate it before we fully understand it, and this would be a loss for science. So strict procedures must be followed to prevent harmful contamination, balancing exploration with responsibility. As the years pass in our unfolding narrative, small bases could grow into larger settlements, with underground tunnels, research labs, manufacturing units using local materials, and perhaps even children born under the pinkish Martian sky, representing the first true Martians in human history, and their bodies might adapt differently to lower gravity, raising new biological questions. And communication networks between Earth and Mars might become more advanced, possibly using orbiting satellites to maintain constant contact, though still with unavoidable delay due to the speed of light limit. So, is this still a daydream? Or is it approaching reality? The answer becomes clearer when we observe that many required technologies are already in testing phases, from reusable rockets to oxygen production experiments, from long-duration space missions to autonomous robotics. And while major gaps remain, the path is no longer pure imagination, but a series of engineering steps, each one measurable and improvable. And history shows that exploration often begins with small outposts before turning into permanent settlements. As seen in the age of sea exploration on Earth, though space is far harsher and less forgiving, and therefore progress will likely be slow and careful rather than fast and dramatic. In the closing moments of this part, picture a quiet Martian evening inside a habitat, with a small group of settlers sharing a meal grown in their own greenhouse, powered by energy captured under a distant sun, protected by walls built from alien soil, and outside the thin atmosphere allows stars to shine brightly. And in that silence, humanity stands on two worlds at once, still deeply connected to Earth, yet beginning to stretch its roots into the solar system. And whether this becomes a strong branch of civilization or remains a fragile experiment will depend not only on technology, but on wisdom, unity, and patience, because Mars will not forgive carelessness, but it may reward careful determination with the greatest chapter of exploration in human history. The first settlement on Mars is no longer just a landing site, but a slowly growing outpost, and the early excitement of arrival has faded into the steady rhythm of survival, where every day begins with system checks, oxygen levels, pressure seals, power storage, and greenhouse humidity readings, because on Mars small mistakes can quickly become deadly, and this constant awareness changes the mindset of the settlers, making them more disciplined and careful than most people on Earth have ever needed to be. And over time, the colony begins to expand, not outward in open air, but inward and underground, because scientists have concluded that the best protection from radiation and extreme temperature changes is beneath the surface, where thick layers of Martian soil and rock can act as natural shielding. And so robotic machines dig tunnels and carve chambers, slowly transforming cold red ground into human living space. And inside these tunnels, lights glow softly, plants grow in vertical farms, and the sound of air circulation replaces the silence of the Martian desert. With each passing launch window from Earth, more cargo arrives, bringing advanced tools, medical supplies, replacement parts, and new settlers chosen carefully for their skills and mental strength. And selection for Mars becomes one of the toughest processes in human history, because settlers must be healthy, adaptable, intelligent, emotionally stable, and able to live in close quarters with others for years. And training programs on Earth simulate isolation using desert bases, underwater habitats, and Arctic stations, preparing candidates for the psychological reality of Mars, where stepping outside requires a spacesuit and where the horizon always glows red under a thin sky. The issue of gravity becomes more visible as months turn into years, because although Mars has gravity, it is much weaker than Earth's, and scientists carefully monitor bone density, muscle strength, heart health, and blood circulation of settlers, and exercise becomes a daily requirement, not a choice, with special machines designed to simulate higher resistance. And medical teams study whether medicines, diet adjustments, or artificial gravity habitats might be needed in the future. And the question of children becomes serious, because if families begin to form on Mars, no one yet knows how pregnancy and early development would be affected by lower gravity and higher radiation exposure. And ethical debates continue back on Earth about whether it is right to raise a new generation so far from their home planet. Economically, the colony begins searching for ways to reduce dependence on Earth funding, and research labs focus on developing new materials from Martian soil, extracting useful metals, and experimenting with manufacturing spare parts using advanced 3D printers. Because every object that does not need to be shipped from Earth saves enormous cost and risk, and there is also growing interest in scientific discovery, as Mars offers unique opportunities to study planetary evolution, climate change, and the possibility of ancient life, and such discoveries could reshape our understanding of the solar system and even the origins of life on Earth. And this scientific value becomes one of the strongest justifications for maintaining a permanent presence. Meanwhile, the dream of terraforming Mars continues to appear in public discussions, especially when figures like Elon Musk speak about releasing greenhouse gases to warm the planet or using massive mirrors in orbit to reflect sunlight onto the surface. But deeper scientific analysis shows that Mars may not have enough accessible carbon dioxide trapped in its soil and ice to create a thick atmosphere, even if all of it were released, and without a magnetic field, the solar wind would again slowly strip away any new atmosphere over time. And so most experts agree that full terraforming is far beyond our current century's abilities, meaning the human life on Mars will likely depend on controlled environments for generations. And this reality shifts the focus from changing the planet to adapting ourselves and our technology to its conditions. Social structures begin to evolve within the colony, because any permanent settlement requires rules, leadership, and conflict resolution systems, and early governance models might combine direct democracy with strict safety laws, since one person's mistake could endanger everyone. And debates arise about independence as communication delays and physical distance make Mars increasingly self-reliant, and some settlers begin to see themselves not just as visitors from Earth, but as pioneers of a new branch of humanity, and cultural identity slowly forms around shared hardship, shared goals, and the powerful image of living on another world. Technology continues to improve, as nuclear power reactors designed for space provide stable energy unaffected by dust storms, and advanced recycling systems approach nearly complete water and air reuse, and artificial intelligence assists in monitoring systems and predicting failures before they occur, reducing human workload and increasing safety. And robotic explorers continue to search beyond the colony perimeter for underground ice and mineral resources, mapping the surrounding region like early explorers mapping new continents on Earth, though always under the awareness that Mars is not a living ecosystem to conquer, but a fragile environment to respect. Back on Earth, public opinion shifts over time, with some seeing the Mars colony as humanity's greatest achievement and others criticizing its cost and risks, and global cooperation becomes essential, because no single nation can easily carry the financial and technical burden alone, and partnerships between governments and private companies expand, sharing data and resources. And international agreements are drafted to prevent territorial conflict on Mars, recognizing it as a shared human venture rather than a place for national rivalry. As years pass, the first emergency tests the colony's resilience, perhaps a major dust storm lasting weeks, reducing solar power and covering equipment with fine particles that infiltrate seals and joints, and settlers must rely on stored energy and careful rationing, working together under stress, and when the storm finally clears and systems remain intact, confidence grows that survival is possible not just in theory, but in practice, and this moment becomes a turning point in human history, proving that a community can endure on another planet. So is Mars colonization still a dream, or has it crossed into reality? The answer becomes more solid as each technical milestone is reached, as reusable rockets lower costs, as life support systems improve, as in situ resource utilization move from experiment to routine operation, and yet the scale required for a self-sustaining civilization remains enormous, requiring thousands of people, diverse skills, stable reproduction, economic exchange, and long-term planning in this transformation. From outpost to true civilization may take many decades, perhaps even a century, but history teaches that great changes often begin with small, determined groups willing to face uncertainty. In the final image of this part, imagine a child standing inside a transparent dome, looking out at the red horizon while learning about oceans and forests on Earth through digital lessons, understanding that their life bridges two worlds, and realizing that humanity's story is expanding beyond one planet, not as a sudden escape from Earth's problems, but as a careful extension of human presence, built step by step through science, courage, and cooperation. And the red planet, once only a wandering star of ancient myths, now holds footprints, voices, and the steady heartbeat of a new human chapter unfolding under a quiet alien sky. We step back and look at the full picture that has unfolded before us, from the ancient sky watchers who saw Mars as a red wandering star, to the robotic explorers that rolled across its dusty plains, to the bold modern visionaries like Elon Musk, who speak about making humanity a multi-planet species. And we realize that colonizing Mars is not a sudden leap, but a long chain of steps built over centuries of curiosity, science, failure, learning, and courage. And when we define Mars clearly, we understand it as the fourth planet from the Sun, smaller than Earth, colder, with weaker gravity, a thin carbon dioxide atmosphere, no breathable air, no natural magnetic shield, and powerful radiation reaching its surface. And yet it also holds frozen water, ancient riverbeds, massive volcanoes like Olympus Mons, deep valleys like Valles Marineris, and signs that billions of years ago it may have been warmer and wetter, which keeps alive the question of whether life ever existed there in simple microbial form. And this scientific mystery alone makes Mars worth exploring deeply. We have seen that the distance between Earth and Mars changes constantly, sometimes as close as about 56 million kilometers, and sometimes far more distant, and that even with our best chemical rockets, the journey takes 6 to 9 months, exposing travelers to microgravity and radiation, meaning that transportation itself remains one of the great challenges. Yet modern reusable rocket systems, advanced navigation software, and ongoing spacecraft development show that humanity has moved from theory to active preparation, and landing heavy human missions safely on Mars is difficult but not impossible, requiring improved heat shields, propulsion systems, and careful engineering, and step by step these technologies are being tested and upgraded. Once on Mars, survival depends on life support systems that create oxygen from carbon dioxide, recycle water almost completely, grow food in controlled environments, and protect settlers from radiation and extreme cold. And experiments like oxygen production tests on Mars have proven that local resources can be used, which means colonization does not require carrying every breath of air from Earth. And underground habitats or soil-covered domes can provide shielding, while nuclear or solar power systems can supply energy, and none of these ideas are pure imagination anymore. They're engineering problems with real prototypes already under study. And this is the difference between fantasy and science. Fantasy has no working models, but Mars exploration already has working pieces slowly coming together. Yet challenges remain serious and cannot be ignored. Radiation exposure over many years could increase health risks. Lower gravity may weaken bones and muscles and affect future generations in ways we do not fully understand. Psychological stress from isolation and distance from Earth could test human relationships and mental strength. Economic sustainability is still uncertain because building and maintaining a colony would cost enormous amounts of money, and terraforming Mars into a second. Earth is far beyond current capabilities and may remain so for centuries, meaning early settlers would live inside controlled habitats, always dependent on technology, always aware that one major system failure could threaten lives, and this constant risk makes Mars far less forgiving than Earth, reminding us how naturally protective and balanced our home planet truly is. So is colonizing Mars daydreaming or realistic progress? The final honest answer is that it is neither simple fantasy nor guaranteed success. It stands in a middle space where science has advanced enough to make small-scale settlement technically possible within the coming decades, but not yet easy, not yet self-sustaining, and not yet safe in the way life on Earth is safe. And success will depend not only on rockets and machines, but on global cooperation, wise leadership, long-term funding, ethical responsibility toward possible Martian life, and a deep understanding that colonizing Mars is not an escape from Earth problems, but an extension of human civilization that still depends on Earth for knowledge, culture, and support for many years. As we close this journey, imagine a future seen many decades ahead, where a modest but stable Martian city exists beneath protective domes and underground chambers, powered by reliable energy, producing much of its own food and oxygen, connected to Earth by regular transport missions, and children born there learn about both planets as parts of their identity. And at the same time, Earth continues to thrive and improve, having learned sustainable technologies partly developed for Mars missions. And in this balanced vision, Mars is not a replacement for Earth, but a partner world, a research base, a backup home, a symbol of what humans can achieve when they combine imagination with discipline. The red planet that once inspired myths of war now becomes a symbol of survival and unity, proving that humanity can stretch beyond its birthplace without abandoning it. And the journey to colonize Mars teaches us as much about protecting Earth as it does about exploring space. Because when we understand how hard it is to build even a small living system on Mars, we gain deeper respect for the natural life support system we already have here. And so the final conclusion of our story is clear.